more problems from related rates just because it's, a challenging section and I want you to have plenty of examples. So we're going to do 3 more, and it's going to start with problem number E, which talks about the rate at which a snowball melts. Now, I always think of these things as like ice cream melting, but yeah, they're going to do a snowball melts. And it gives me a chance to remind you or show you of a little relationship here. Example E. We've got the volume of a sphere is 4/3 pi r cubed. I think Archimedes came up with this formula a couple thousand years before Newton ever conceived of calculus. So we want to know if a snowball melts so that the surface area decreases at a rate of 3 centimeters per second, find the rate at which the diameter decreases when the diameter is 11 centimeters. So, okay. Now, this formula talks about the volume. But if you think about how the volume of a sphere changes, think about blowing up a balloon or inflating a basketball, the volume is changing right at the surface. So the change in the volume with respect to the radius is actually going to give you the surface area. So let's differentiate this with respect to r, and that v prime of r is actually going to be the surface area. What's the derivative if I differentiate with respect to r? What's the derivative of this? Well, the 4/3 and the pi are both constants, right? I don't have to use a product rule or anything like that. So what happens when I differentiate this term? Yeah, the 3 is going to come out front. It's going to cancel with the 3 in the denominator, so you're going to get 4 pi r squared. And so that's literally exactly how I remember the formula for the surface area. Now you can actually see a similar thing going on when you look at the area of a circle. Area of a circle, you don't have to copy this down, is what? Pi r squared, right? But if you're changing that area, that change is going to take place at the circumference. And take a look what happens when you differentiate this with respect to r. A prime of r, what's going to be the derivative of this? Come on, make me look good. We're on camera. Thank you, 2 pi r. But where do you know this 2 pi r from? What's that give you? Yeah, the circumference of a circle. So you're seeing the same kind of thing happen. And it's kind of interesting that they can actually find the volume of figures you can't even see, that of spheres in the 4th dimension and higher. They have formulas for that. But fortunately, we don't have to go there. Let's stick with what we're going to work with here, which is finding the volume, finding the rate at which the diameter is decreasing. Okay. So let's see, we've got this formula. Find the rate at which the surface area is decreasing at a rate of 3 centimeters squared per minute. So that's going to be something we want to take care of. What is that telling me here? Oops, sorry, I didn't realize it wasn't on there. What's that telling me in terms of our problem? We've got S of r is 4 pi r squared. What's this mean relative to our problem? All right, something's in a minus, and I like that you get the minus 3, and that's going to be centimeters squared per minute. But what should I put on the left-hand side? What do I want to label that? ds dt. Perfect. So it's the rate at which the surface area is changing in units of time, so it's going to be ds by dt. Nice. Nice. Now they want us to know, how that's changing when the diameter is 11 centimeters. So the diameter is 11 centimeters, but we don't really use the diameter in this formula, do we? What do we use instead? use the radius. So what's the radius? Yeah, 11 over 2 or 5.5. That's going to be in centimeters. Great. And they're asking us to find the rate at which the diameter decreases. So we want to know d, and I'll use a capital D for diameter, dd by dt. And I hate using the same letter, but it just fits so good here. So I use lowercase and uppercase, so hopefully it won't make a big deal for us. That's our unknown. Now the big thing in these problems is that you're going to have to find an equation that allows you to substitute in for ds by dt, dd by dt, etc. We're not quite there. We would be there if we took time to rewrite this in terms of a diameter. I don't feel like doing that, so we'll work that out at the end. What we'll work for is trying to find dr by dt, and then we'll get the dd by dt from that. So let's take this equation, s equals 4 pi r squared, and differentiate it with respect to time. So I want d by dt of that. Now we're going to have to be a little bit careful when we differentiate this term here. You're going to have to use the chain rule. On the left-hand side, we get a very predictable ds by dt. But what's going to happen on the right-hand side? What am I going to get? 8 pi, good, because the 2 is going to come out in front here. Multiply 8 pi times the derivative of this, which is going to be r to the first power, I'll just write r, times the derivative of the inside. I put brackets on this to remind you you're going to have to differentiate implicitly dr by dt. We know pretty much all we need to know here. We know ds by dt is minus 3, 8 pi. We know that r is 5.5. So let's put in a 5.5 here. And, well, we don't know dr by dt, but eventually dr by dt is going to help us find dd by dt. R by dt. So it's going to give me what? 44 pi dr by dt. And then I'll just divide. Negative 3 over 44 pi equals dr by dt. Unfortunately, this was set up with the radius. So now I got to figure out the relationship between dr by dt and dd by dt. So let's finish that off. And I'll do that right here. How do the diameter and radius relate to each other? How do you get from one to the other? Yeah, diameter is twice the radius. So if I differentiate this with respect to t, dd by dt, I'll get dd by dt equals 2 times dr by dt. And I know what dr by dt is. It's this. So I'm just going to plug this in here and get my answer for dd by dt. 2 times negative 3 over 44 pi. The 2 will cancel, I'll get negative 3 over 22 pi. And that's going to be in units of centimeters, centimeters per minute. Let's not forget their units on that stuff. Nice. Pretty small overall. I mean, that's not going to be a, it's going to be, I don't know, let's see, about 0.04 something, 0.045 maybe, centimeters per second. So not a big amount, but that's neither here nor there. Are we okay with our work on this one. Yes, Simon?
I do have one question about like the units. It's okay to just add the units at the end instead of having them throughout the...
That's a great question, the units. I fight with myself, I mean, because it'd be nice to show you that all the units cancel out and drop out and you end up with the right thing, but it becomes a real pain.
Yeah.
And you'd probably look at that and go, ugh, it would probably make your head spin if you're trying to keep track of all the units. So I just make sure that I put the right units in at the end and that the units make sense. Now, how come, speaking of units, how come I don't have centimeters squared here per minute? What would be wrong with that? Centimeters squared you'd associate with what kind of calculation? Area. We're not looking at area, we're looking at length. Length has one dimension, area would have two dimensions, volume would have three dimensions. So, at least our units match what we expected, which would be centimeters per minute. So, feeling good about that one. Yeah. But no, I struggle with that. It'd be nice to show you that they cancel out and stuff like that, but it's just not really worth it. So, all right, great question. Great question. Anything else on this one? Let's move over to example G. And we'll try and draw ourselves a good picture for this as well. The lighthouse is located on a small island 3 kilometers away from the nearest point P on a straight line, on a straight shoreline, and its light makes 4 revolutions per minute. How fast is the beam of light moving along the shoreline when it's 1 kilometer away from P? So, all right, a lot going on there. And like I said, a good picture will help out a lot in this one. So, and for a decent picture, I'm going to pull out a ruler. Give me a second here. This little thing is stuck. Ah! There we go. Okay. So, example G. So we've got our lighthouse and a point on shore. That distance is 3 kilometers. 3 kilometers. And the lighthouse is rotating. So you've got some angle here, theta. And it's rotating such that the light makes 4 revolutions per minute. So I want you to think about that. 4 revolutions per minute. Let's see if we can't figure out a couple things to write down from this. Probably want to keep track of the fact that this is 3 kilometers away from a point P on the shore, and we want to know how fast the beam is changing when the shoreline, or when it's one kilometer from P. So some other point here. I'll call that one N, because I promised Nicole that I would remember to call on her today. She's big smile from Nicole. She's excited about that. All right. So that's 1 km. So, all right. Let's think. What can I write down for this information right here? That one's going to be kind of tough. That's where we got to work hard. How would I summarize this information? The light makes 4 revolutions per minute. Well, maybe remind you of something. 1 revolution in radians. 1 revolution means you're going all the way around the circle. How far is 1 lap around the circle in terms of radians? That's in degrees. What about radians?
2 pi.
2 pi, right? So 1 revolution is 2 pi radians. So what about 4 revolutions. 4 revolutions is 8 pi radians. And we're doing that 8 pi radians per minute. Now that last little bit here, per minute, that's screaming out something to you that you should kind of pay attention to. It's a rate. And rates in our class are denoted by derivatives. So, all right, it's going to be the derivative of something. What's it the derivative of? Well, it's the rate at which the angle is changing. So how should I write that here? d theta by dt. That's what I was looking for. d theta by dt is 8 pi radians, 8 pi per minute. Okay. Nice. Now, this side is fixed. It's not changing. But as the light rotates, around its axis, the point on shore that it's pointing at will change. So this is a little bit of a variable. Call that x. And x, we're going to look at it when x is 1 kilometer. But in order to have some relationship that I can work with, I needed to figure out something I can differentiate. I need to differentiate something that involves theta. So let's think back to our trigonometry. What can you think of that it would involve the theta, 3, and the x here? Do not say Pythagorean theorem. I'll scream. Pythagorean theorem doesn't involve theta here. Tangent, yeah. Thank you, Ashley. So the tangent of theta, remember, tangent is what over what? Yeah, remember SOHCAHTOA. Tangent is opposite over adjacent. So the opposite side would be x. The adjacent side would be 3. X over 3, like that. Now it's up to you where you want to keep the 3. You could write it as 1/3 x. You could move the 3 to the other side. Doesn't really matter so much. I'm going to move it out in front. 1/3 x. Tangent of theta. What has to happen next, and happens in every related rates problem? What do we have to do in order to proceed? Yes, we have to differentiate implicitly. So I want d by dt here. And let's kind of mark off a few things that we have to be careful about. We're differentiating with respect to t, not to theta, not to x. So you're going to have to use the chain rule on both of these things. So give yourself a shot at that. What does this look like in terms of a derivative? So work on those two. If you're watching this later, then pause it, see if you can't come up with the derivatives here. A few people are like scratching their heads about derivative of tangent. Somebody help out. What's derivative of tangent? Secant squared. There you go. So it's going to be derivative of the outside. Derivative of the outside you just gave me, that was secant squared of theta times the derivative of the inside. So you got to use the chain rule here. What's the derivative of the inside? Nicole, what's the derivative of the inside, please?
Just 1 times d theta dt.
D theta dt. Well done. All right, d theta dt. And keep going if you wouldn't mind. What's the derivative on the right-hand side going to be?
1/3 times dx dt.
Yeah, perfect. 1/3 dx by dt. So let's get a d theta by dt in here that looks reasonable. And then 1/3 dx by dt. Nice. Let's look back at the problem. It says, how fast is the beam of light moving along the shoreline when it's 1 kilometer from P? All right, well that's going to be something else that we're going to be looking for. The beam of light moving when it's 1 kilometer from P. What would I represent that as? What is it in terms of our problem? What notation should I use? So that's this right here. You're sweeping the floor or the shoreline with the light. How fast is it moving? So what is it that we're looking for in this one? No, not the second derivative. Dx by dt. It's how fast is this changing with respect to time. So how fast is it moving? So it's going to be your dx by dt is unknown. That's what we're looking for there. So good to know. Let's see. We're going to actually need to figure out, I think, what theta is. They don't exactly tell us what theta is, do they? No, they don't. So we're going to have to do a little bit of work to figure out what theta is, but we can do that. So let's come over to here. We know that x is 1 kilometer, and then when x is 1 kilometer, I get tangent of theta equals 1/3. So how do I solve for theta? Yeah, the inverse tangent. Awesome. Ashley got an A in her trig class. At least it seems to me. All right, so inverse tangent of 1/3. That's going to give us our theta. Probably going to want a decimal value from that, from our calculator. I'll just keep that around. Maybe there's a fancy way I can work around not using it. Inverse tangent of 1/3. Make sure your calculator is set in radian mode. It should be set in radian mode pretty much for the entire class. So about 0.23 or 3218 maybe. Approximately 0.3218, rounding it to the 10,000th place. Should be close enough. And I think we've got everything we need to fill in here. So we're going to solve for dx by dt by multiplying both sides of this relationship by 3. So multiply that by 3. That's going to give me 3 secant squared of theta, d theta by dt equals dx by dt. So let's plug that in and see what we can get. So it's going to be 3 times secant squared of 0.3218 times d theta by dt. And d theta by dt was 8 pi per minute equals dx by dt. Now, if you're going to get a decimal value out of this, it's going to take a little bit of thought. Your calculator does not have a secant squared button, nor is the way to calculate that the inverse cosine. What do I have to do to calculate secant squared on my calculator?
1 over sine.
Close. Try again.
1 over sine squared.
Cosine. Yeah. So 3 times 8 is 24 pi. And then you're going to have to do cosine squared in the denominator, 0.3218. And that's going to be my dx by dt. Even this is a little bit of a pain. Your calculator doesn't recognize that notation. If you're going to do this, you're going to have to do that as 24 pi over cosine of 0.3218 parentheses squared. And for my part, I'm going to use the A and S key from the calculator. That way I don't have to type that in, and I'll get an exact value. So let's take a look at that on our calculator. And I'll clear out all my buttons here. It's probably easiest in this one to have a nice horizontal fraction. So I'll hit the alpha key, then the X key, and put in 24 pi in the numerator. And then parenthesis cosine of my previous answer. My previous answer was the inverse tangent of 1/3. I don't feel like typing that in, so I'll hit the second key, then the opposite key. That way it's got my previous answer in there. I need 2 parentheses. One closes off the cosine, the argument of the cosine, the other one closes off the denominator, and then I want to square that thing. So there you go. 0.8378, we'll call it. 0.78. I'm trying to think about the units though. That's a dx by dt. That's got to be kilometers per minute. Kilometers per minute. Because x is in units of kilometers, and our rate was in, units per minute, so that's going to be kilometers per minute. So it's a little bit more than 52 miles an hour someplace. So pretty fast, but then again, it's turning very fast, and it's a little bit far away. Whew. Okay. Comments on example G here. We're going to do one more. Yes, please.
Question.
Yes, please.
How did you go from 3 secant squared of 0.332?
Down to here?
Yeah.
Sure. I did the 3 times the 8 pi. They gave me the 24 pi.
Yeah.
And secant squared is 1 over cosine squared. So I rewrote cosine squared, I rewrote secant squared as 1 over cosine squared. So that's where I got that cosine squared term in the denominator.
Okay.
All right?
Thank you.
Yeah, no, thank you. Last but not least, and Marcus, I picked this one with you in mind because of our conversation the other day. 2 cars start moving from the same point. One travels south at 56 miles per hour. The other travels west at 42 miles per hour. So going south, going to some nice warmer weather. Going east, no, you're going west. All right. I don't think there's anything good out west at the nearby westward toe, but whatever. So let's write down a nice little graph for ourselves. For a second, I thought I was going east, and I was like, I don't think I want to be driving east right now. They're getting a lot of snow. Did anyone catch the snow total? They were supposed to get over a foot in New York City and New Jersey. I didn't either. So, all right. I probably shouldn't have tried to draw this to scale. I didn't do a good job of it either, but all right, so we got a few variables. I'm just going to call these X, Y, and Z for lack of something better. And what information do I have about X, Y, and Z? Oh, let's see. It's kind of subtle here. Yes?
Wouldn't the 42 and 56 be dx and dy since it has the whole
Nice.
per hour?
So let's see. One's traveling south at 56 miles per hour. So that's going to be your dy by dt is 56 miles per hour. Nice. What else can you tell me about this one? What else do we know? What are we looking for? What do we know? dx by dt is 42 miles per hour. And dz by dt. What's dz by dt? Yeah, we don't know that. Okay, we're still going to be stuck figuring out some things here. But we got a couple of the important ones. What else do I need to know? What else am I going to need in a problem like this? How far they are from where they started. And how are we going to figure that out? Not. Yeah. On a roll. Way to go. Yeah, they're traveling for 2 hours. And they go 56 miles per hour for 2 hours or 42 miles per hour for 2 hours. So what are these distances then? Let's start out with the 56 miles per hour. Somebody's in a hurry to get down south. So that's going to be what? 112 miles. 112 miles. And then over here, 84 miles. So you're just using distance equals rate times time. So distance equals rate times time. 56 times 2, 42 times 2, great. But that doesn't tell us what z is yet. How are we going to find z? Justin, any suggestions?
Use Pythagorean theorem.
Yeah, just the Pythagorean theorem. 84 squared plus 112 squared equals z squared. So z is going to be the square root of that. And personally, when I do this for myself, I never really bother to calculate those numbers out. I just go for the whole thing. So square root of 84 squared plus 112 squared. Oh, wow. Worked out nice and even. That makes this a Pythagorean triple. Pythagorean triples are kind of rare. So numbers like 3 squared plus 4 squared equals 5 squared. I'll be honest, I didn't expect a nice even number to work out on this one. So 140. Let's put that in. Okay. So now what? We're looking good here with all of this stuff, but I don't have anything to plug this into, do I? How am I going to get something to plug that into? What should I do? Well, in the last couple problems, I had something that I could differentiate. So I would do d by dt. I would take the derivative with respect to time of something. But what's that something in this problem? They didn't give it to us. Amir, any suggestions? Marcus?
Would it be the Pythagorean theorem?
Yeah, it's just going to be x squared plus y squared equals z squared. Nice. Now keep in mind that you have to differentiate this implicitly. you're not differentiating with respect to x. You're not going to get just 2x, right? You got to be the derivative of the outside times the derivative of the inside.
It would be 2x dx dt, and repeat it with the y and t, basically.
Yep, 2x dx by dt plus 2y dy by dt equals 2z dz by dt. And if you want, you can divide out all the 2's. So you're just left with x dx by dt plus y dy by dt equals z dz by dt. But unlike some of our other problems that we did the other day, I think we maybe did one problem like this, none of these are 0, right? We're trying to figure out what z is, so we're going to fill in everything else. That's going to be x was 84 times 42 plus y is 112 times 56 equals z, which was 140 times dz by dt. All right. So let's figure out the left-hand side. So 84 times 42 plus 112 times 56. Somehow or another, I feel like there should be something clever that I could do here. And then we're going to divide that by 140, and we get 70. So we end up with 9,800 equals 140 dz by dt. So 70 equals dz by dt. What units should I plug in with that? Miles per hour. Miles per hour. Does it make sense that it's positive? Should it be positive or should it be negative?
Because it's a distance.
As you're moving farther south and moving farther west, what's going to happen to the distance between you? Is it going to get smaller or larger?
It's gonna get larger.
It's going to get larger. So it makes sense that dz by dt is positive. That sign in this problem reflects the fact that the distance is growing larger. Antonio, I think you had a question?
Well, why the two in front of each get removed?
I just divided everything by 2.
Oh,
Yeah, you could leave it there. It'd be fine. It just feels like more work to put it in there than to divide it out. So, yeah, good question. Amir?
What are you deriving with respect to when it's x squared plus y squared equals z squared?
We're differentiating with respect to t, because this is all changing with respect to time. So if we were differentiating with respect to x, then you just get 2x here. But then here you get 2y dy by dx and then 2z dz by dx. But in this case, this variable doesn't match any of these, which is why we got all these differential terms. So good question. Yes?
So when we are working with a right triangle, we will always end up at some point with x times dx dt plus y times dy dt equals z times dz.
Yeah, your Pythagorean theorem problems do end up like this. But be careful, not everything turns into a Pythagorean theorem problem, like the last one. All right? And I think there's another one in the notes here about walking away from a street lamp where you've got to use similar triangles here. Yeah, street lamp. You got to use similar triangles to set things up that way and use, proportions. So it's something like this. You got a man 6 feet tall, and he's walking away. So you label this distance x, and maybe this one h or something like that. But you got to set up similar triangles there. So not everything that involves a triangle is going to be a Pythagorean theorem problem, but a lot of them are. So I wouldn't be surprised to see a Pythagorean theorem problem on an exam. But the key thing that I look for in all these things when I grade your homework or grade your exams is that you're differentiating implicitly. without implicit differentiation, it's just wrong. I can't even in my most charitable moments, we just won the gold medal in hockey moment, when say, yeah, I'll give you partial credit there. No, you're really missing the point of these problems if you're not differentiating with respect to time and differentiating implicitly. So that's where it all starts, okay? Good question on that one. All right, that's it for 3.9.